Welcome to the live space launch of CUAVA-1 on the 28th of August 2021. CUAVA-1 is the first satellite developed by the ARC Training Centre for CubeSats, UAVs and their applications. In a few moments, we will begin with a welcome by the CUAVA Director, Professor Eva Cairns, and presentations by the CUAVA-1 engineering and payload teams. Before we begin, CUAVA would like to respectfully acknowledge the traditional owners of the land on which we stand today, the Gadigal and Wangal people of the Eora Nation, and pay respect to the traditional owners of all the lands on which CUAVA research is undertaken.
Hello and welcome. I'm Professor Eva Cairns, Director of the Australian Research Council's Centre for CubeSats, UAVs and their applications, otherwise known as CUAVA, and Professor at the University of Sydney. It's my great pleasure to welcome you on behalf of the entire CUAVA team to this event, a deliberately informal launch party for CUAVA's first satellite, CUAVA-1. This event celebrates the launch of CUAVA-1 into orbit to the International Space Station, nominally at 5:37 p.m. on Saturday, the 28th of August. You can see here CUAVA going up into orbit figuratively. So we're going to proceed by having a discussion of the big picture of CUAVA by me, followed by a description of the satellite itself by Dr. Shirley-Ann Bai, who's the Training Centre engineer, followed by brief presentations by the instrument teams, short Q&A period, and then the countdown to the launch itself. So what is a CubeSat? CubeSat is a satellite built up of cubes, which are 10 centimeters on a side, each one forming one unit. CUAVA-1, which you see here, is a 3-unit CubeSat, weighs about 2.8 kilograms. Why is it important? Well, it's our first CubeSat, the first one for CUAVA, and it addresses 4 foci via 4 payloads and 2 separate technology demonstrations. So a very sophisticated spacecraft. First one is focused on Earth observations and the Tolaboy astrometric instrument, otherwise known as AEST. There's a GPS instrument called KIA from the University of New South Wales. There's a space weather instrument, which is a radiation counter, looking at energetic particles hitting the spacecraft. And then a reconfigurable electronics instrument called RUSH, and then the technology demonstrations, which are a data over power network and a solar cells from our partner, Airwave Communications. We're going to launch to the ISS today on a Falcon 9 mission SPX-23 from the Cape. The contracts with SpaceBD, which then is to JAXA, the Japanese Space Agency, and then SpaceX, and you know the nominal launch time. The deployment from the ISS actually into space for CUAVA will nominally be in the first week of October. We have special thanks to many groups, including those here, and the CUAVA team, of course, especially Shirley-Ann Bai, Duncan Un, Rain McMillan, and Helen Brown. So what is CUAVA? CUAVA, as we mentioned, is an Australian Research Council training centre for CubeSats, Uncrewed Aerial Vehicles or UAVs and applications. It involves 11 chief investigators and 12 partner investigators. Andrew Dempster's the deputy director from the University of New South Wales. Eleanor Bruce from Geosciences at the University of Sydney is the assistant deputy director. And our focus is developing a world-class Australian space industry in CubeSats, UAVs and their applications. These are the partners: University of Sydney, University of New South Wales and Macquarie University. We have 4 companies: Airwave Communications, Arbor Carbon, High Vista and Sabre Astronautics, and 3 government labs, the Bureau of Meteorology, and 2 divisions of the Defence Science and Technology Group, both maritime and also intelligence, surveillance and reconnaissance. And then we also have the Rochester Institute of Technology from the United States. So we're nominally a 5-year training centre, starting in very late 2017, going to the end of 2022, but due to COVID, we expect an extension to the end of 2023. About $6 million in the centre, but then we're looking for new grants, including Waratah Seed from the New South Wales Government. We have multiple elements, 5 postdoctoral fellows for one, many students, 13 PhDs, 3 masters, 2 honours and 25 undergraduates at least so far. We're expecting to have 2 to 3 CubeSats over our lifetime and 1 UAV or aircraft campaign per year. So our goals are to train the next generation of workers in cutting-edge advanced manufacturing, entrepreneurship and commercial space and UAV. So it's human capital primarily, but then developing new instruments, technology and products to solve particular problems and helping to develop a world-class Australian space industry. We have 3 themes, systems, instruments and products. These ones both CubeSats and UAVs. These ones primarily CubeSats. 12 projects, and CUAVA-1 involves CubeSats, of course, itself, images and hyperspectral images to be precise. Also remote sensing applications. There's GPS as well, and space weather. So these are the aims and interests of CUAVA. So here we of course have our satellite. It's properly an Australian one, so down under from the point of view of the Northern Hemisphere. And we are ready to go. Here we are at the Advanced Instrumentation Technology Centre at the ANU, and then just undergoing our final thermal vacuum and vibration tests. And here we are being accepted by JAXA and Space BD just about 6 months ago. So here we are. We're looking forward to being in space, and we look forward to discussing it with you. Thank you.
Hello, everyone. Welcome to the CUAVA-1 launch event. It's nice to see you all here witnessing the CUAVA-1 launch. It's quite fortunate that we can't physically be together. I hope you all have a glass of wine or some alcohol in hand. I, for one, be using all kinds of cues to drink since lockdown. Last night, I was trying to open a bottle because I heard my neighbor was singing a happy birthday song. Of course, but then my wife told me I can't claim they're my close family just because we live really close to them, which I think is really unfair. So anyway, here we are. It's been a very long journey since where we started. The CUAVA-1 satellite is the center's first CubeSat mission. It's a 3U satellite mission. Let me show you some pictures. The CUAVA-1 satellite is the center's first CubeSat mission. The satellite carries 2 first-generation instruments for our future Earth observation missions. The first one is the imager spacecraft and Tanito instrument, named AEST, designed by the University of Sydney. It contains a RGB camera, a hyperspectrum core, and a Tanito instrument for the breakthrough condition to look at the stars. The payload is the first iteration towards a CubeSat-ready hyperspectral imager unit. We also have a GPS unit designed by UNSW. It's a pathfinder mission for the future radio reflectometry mission that is using the reflected GPS signal to measure the seed state. We also have 2 payloads for technical demonstration and in-orbit experiment. We have a radiation counter and a data over power bus payload developed by the University of Sydney, which is used to first measure the space weather while the radiation environment in low Earth orbit. Secondly, demonstrate a novel data over power bus solution on CubeSat. We also have an in-orbit reconfigurable FPGA system in space, namely Rush, to enable FPGA-based off-the-shelf hardware without compromising reliability. The rest of the satellite is built on commercial off-the-shelf component. The CUAVA-1 mission also carries the objective to validate our flight software, which we designed based on an open source platform. The idea is to use the same or similar hardware for the future satellites to shorten the development process. As for the ground station, we got Sabre team develop a software-defined radio-based ground station radio. We're going to connect that to the ground station at the University of New South Wales, supported by June's team, and use the ground station to track the CUAVA-1 satellite. Integration and testing. The integration of the CUAVA-1 satellite started in July 2021. We managed to integrate the satellite in just a few weeks' time and went for our first environmental testing. The testing actually went really well, but we then encountered a major setback due to some dimensional issues. JAXA therefore rejected the last round of the safety review, and we were forced to reintegrate the satellite and perform another round of testing. So we did. It took us some time, but we managed to resolve the issue imposed by JAXA and start another round of integration and testing. We also performed the fit check more carefully to make sure this time we comply with the JAXA's requirement. Then we believe we are ready to go. We successfully acquired a launch certificate on the 14th of March. On the very same day, we had put the satellite on the plane to Japan. As you can see, it wasn't a very smooth journey, but as a team, we really learned a lot. More importantly, I think we can claim that we have achieved some very important mission objectives even before the satellite's launch. We have involved more than 25 students in the project. Many of them have contributed in the flight software rebuild, which we will open sourcing soon. We learned a lot from the mission, and we're integrating ourselves into an excellent team. Here, I want to express my gratitude for our team members, Tony Monger, Yu Hao, Patrick, who are working on the satellite side. We got our payload team, Chris, Jun, Edison, Tony Wu, and Xiaofeng and Yijun here, especially Chris and Xiaofeng, who provided lab access for the satellite integration and testing period. Also, of course, we got our excellent Sabre team who have supported the ground station development. Lastly, a special thanks to Eva, who has enabled such an excellent project. Okay, enough from me. Now I'm going to open that bottle of wine my wife saved from my neighbor's birthday and sit back and enjoy the rest of the event. I hope you guys will enjoy it too. Hope next time in the next satellite launch, we can be together and drink together. Bye.
Hello, everybody. Jason Held here, CEO of Sabre Astronautics. I just wanted to say how very proud and happy we are to be a part of this mission. The CUAVA mission is a real big milestone for everybody. Anytime you have a spacecraft that flies, it's a huge deal. We're excited to be a part of it, excited to fly it out of the Mission Control Center out at Adelaide. Best of luck for the launch, best of luck for the flight, and looking forward to seeing its success. Thanks.
Hi everyone, my name is Chris Betters, and I'm the lead developer on the INSTI instrument, which is actually a combination of two instruments. We've got an imager and a spectrograph, and something called the Tiny Tall instrument. Now, both of these are, one of them is a ground viewing instrument, so it's kind of a ground imager, originally meant to be a hyperspectral imager, but it's kind of a test bed for future missions. And the other one is this Tiny Tall telescope, which will point out into space to image binary star systems is the primary goal of it. Then also the actual payload helps host the Kia GPS antenna, and it's all run by a little Raspberry Pi compute module-based board, which actually runs the two image sensors that both instruments use, which are both Raspberry Pi cameras. This is an exploded view of the instrument, just so you can see all the bits that go into it. So there's the imager instrument, which is kind of a little telescope with a beam splitter that helps split the light between the Raspberry Pi camera and our spectrograph, which is actually just an off-the-shelf little instrument from Ocean Optics in this case. The goal is to have around 20 meters spatial resolution with this imager. It's an RGB sensor, and like I said, it's using a Raspberry Pi based camera. And then the Tiny Tall instrument, it's got some similarities in that it's a small little telescope. You can see in this position here, and it's using this funky diffractive pupil, which actually takes the image and makes it terrible. But because we're looking at point sources, this actually adds a bunch of information for us to measure the separation of binary stars more precisely. So the goal of Tiny Tall, it's kind of a precursor mission to a much larger mission, either Talleboy or Tallamin, which will be, tens of centimeters telescopes. And the end goal is to be able to do highly precise astrometry of star systems like the Alpha Centauri system to directly measure the presence of a planet. Here are just a couple images of what the inside of of actually putting together the instrument. So this is me in our clean room over in the Sydney Nanoscience Hub at the University of Sydney, right after kind of putting it all together. So these are the two apertures for the two instruments. There's the big hole where the GPS sensor would sit. It gets integrated a little bit later. This is the inside of it. So the imager telescope, the little spectrograph, one of the lenses for the tiny tall telescope, and then the custom Raspberry Pi compute module carrier. A couple more images here, just looking at it from different angles. You can kind of see inside some of the cables for the various bits, and then once it's actually integrated inside the satellite, so we have it actually sits kind of in the middle here, and it's got the two little apertures, the GPS antenna, and this is actually an image I took of the Sydney Centrepoint Tower, or the AMP Tower, or the Westfield Tower, or whatever it's called these days. Is what I actually used for focusing the instrument, because I needed something very far away and wanted to make it reliable. So thanks for that, and look forward to a fun launch.
The Kia GNSS receiver instrument is our 4th generation GNSS receiver. All generations of this instrument is built from the ground up here at AXA UNSW Sydney in collaboration with a New Zealand affiliate. Our 3rd and 4th GNSS receivers also flew on several defense-related space missions. In 2018, Kia GNSS flew on the first 2 Australian-built CubeSat operational in space, built by UNSW Sydney and USID, seen in the bottom right, which demonstrated operational hardware capability in space. The red board on the top right is our credit card-sized Kia GNSS board. The green board underneath it is our CubeSat PC104 compliant adapter. This way, the Kia can be easily scaled to adapt to various other configurations, such as a phased array. The navigation data retrieved will be formatted in NMEA seen on the left. Next. CUAVA-1 is meant to be a tech demonstrator for the navigation board in a larger GNSS reflectometry payload meant for CUAVA-2. One unique capability that we will demonstrate here is the fast in-orbit GPS acquisition by providing time and location assistance from the ground, much like how cell phone use cell phone tower information to give you instant GPS location. Otherwise, conventional GPS operations will require you to wait minutes or tens of minutes to obtain a valid GPS location. CUAVA-2 is our main mission, which is to perform reflectometry experiment using our space demonstrated Kia GNSS SatNav from CUAVA-1. On the right, the red Kias can be seen as part of our GNSS-R assembly. On the bottom left, we show our prototype GNSS-R payload performing a ConOps test with a real-time display of the delayed Doppler map, DDM, a crucial data product for our reflectometry experiment. This payload can also process and store live DDMs. GNSS reflectometry is a form of bistatic passive radar. Our instrument collects and processes the direct reference signal in tandem with surface reflected signals using a pair of Kia GNSS receivers operated simultaneously. Features of the reflection surface show up as minuscule perturbations in the processed DDMs. Detecting or analyzing these perturbations enables applications including sea wind estimation, altimetry, and sea ice or drift ice detection. More information of our CUAVA-1 payload software can be found in these links. I'd like to also acknowledge the contribution from the rest of our team here, Dr. Eamon Glennon, Dr. Kevin Parkinson, Professor Andrew Dempster, and Ignatius Rivaldi. Thank you very much.
Hi everyone. I would like to provide a brief overview of the Rush payload on CUAVA-1 CubeSat. Rush payload is designed to showcase fault-tolerant reconfigurable systems for space. The primary objective of the Rush payload is to demonstrate and validate new approaches to rapidly recover from radiation-induced single-event upsets in commercial SRAM-based FPGA devices. So we are targeting COTS devices. As you can see on the left-hand side, at the heart of the Rush payload is the Xilinx Arctic 7 SRAM FPGA, chosen for its high logic density to power consumption ratio. It is on Xilinx Arctic 7 FPGA where the experiments take place, and we also have a microsemi smart fusion system on chip flash FPGA acting as the microcontroller unit, which oversees the overall operation of the Rush payload and acts as an interface between the payload and the CubeSat onboard computer. So the Rush payload was designed and built to compare the performance of module and scrubbing-based approaches to SU recovery. Scrubbing is commonly used for SU detection and recovery. With this approach, however, the configuration memory of the FPGA is continually scrubbed, even if there are no errors. With the module-based approach that we have developed, the recovery process is only triggered when there is an error, and we are able to pinpoint the error location and fix that specific part. During the experiments, SU events will be logged by the MCU, and the time, location, and the time to recover will be transmitted to Earth as CUAVA-1 makes its passes over the ground station. We will have both techniques running at the same locations to ensure fair comparison. So we would like to see how module and scrubbing-based approaches compare to one another. It is important to note that all of this would not have been possible without the contributions from a team of academics, researchers, PhD, masters, and thesis students as captured on the slide. I would like to thank them all to make this happen. We are very excited about the CUAVA-1 launch and can't wait to see the Rush payload turned on in orbit. Thank you very much.
My name is Yi Jun. I'm a PhD student at the Space Systems Engineering Laboratory at the School of Aerospace, Mechanical, and Mechatronic Engineering. My PhD topic is data over power bus for satellites. My PhD supervisor is Xiaofeng Wu. This figure is our radiation counter and data over power bus payload for CUAVA-1. It contains a radiation counter array and an experimental version of the data over power bus. The solid-state radiation counter used in this payload is BG51SM, which can detect both beta and gamma radiation. Several detectors together form a detector array to increase the sensitivity and accuracy of the detection. The voltage supplied to the detectors is 3.3 volt. The current draw is approximately 25 microamps. The sensitivity to radiation for each unit is 5 pulses per minute for a 1 microsievert per hour radiation dose. The data over power bus contains 2 nodes. Each node is controlled by a separate ESP32 microcontroller. We collect data from the radiation detector, and the data is encoded at the ESP32 microcontroller and injected into the power line using an injection circuit. Both power and data are delivered to the second node from a single coaxial cable. In the current design, the data over power bus can achieve a speed of 47 megabytes per second. When the CUAVA-1 is in orbit, we will test the radiation counter and data over power bus together. The onboard computer sends a reading request to data over power bus node 1, and the request is then passed on to node 2 through the DOP line. Node 2 gathers reading from detector array and responds to node 1.